So that now we've got the rules and the secrets of the periodic table established based on electron configuration, let's go over that. And first I want to talk about a Russian who wasn't entirely mad.
Did he drink vodka?
He was Russian.
Did he have
Question was, did he drink vodka? Of course he drank vodka. Dmitry Mendeleev first tried to order the then known 50 let me start again. Dmitry Mendeleev, the Russian, tried to order the then known 57 elements in order of increasing atomic mass. This didn't work. The table was all over the place, things were behaving differently, and they weren't organized in groups based on their reactivity or how many electrons they were going to give up or gain. So it didn't really work. Okay? But you have to imagine that the mass was 70 years before neutrons were discovered. So he was working in the dark with a lot of this. He grouped elements with similar chemical properties vertically after that. And when he did that, he noticed some trends. And this is before any of the electron stuff had came to light through Bohr. All right? And in much the same way to our table now, we have it grouped due to similar chemical properties. But we now know that that's dependent on how many electrons are in the outer shells. So if we look at our modern periodic table, it has the elements arranged in order of increasing atomic number as we go across certain rows. Okay? It looks like this. You've got your group 1, group 2, group 3, group 4, group 5, etc. Group 8 with the full shells. The metalloid line. Once you cross that line, you're no longer a metal, you're a non-metal. Okay? So you've all seen that before, hopefully. Now, the Roman numerals across the top are the main group numbers. They represent the number of electrons in the outer shell. I know I've said that 5 times already today. I'll say it once more. And the numerals down the side are the period numbers. They represent the number of shells with electrons in them, though they're not all full. And that black diagonal line you might have heard of before, but again, it just separates the metals on the left from the non-metals on the right. The 8 elements that are shaded near the line are what we call semi-metals. Okay, so when you've got those 8 elements that are standing near the line, they're semi-metals. Germanium is a semi-metal. Aluminium, okay?
It's not completely a metal.
No.
So what defines a metal?
The ability to give up electrons is how we define a metal.
And a non-metal?
The ability to take them.
So aluminium does both?
Aluminium acts more of a metal. It's silicon that does both. Okay? But aluminium can have properties. It holds on to its electrons a bit more than the other metals.
But it has to be one of the others.
Yeah. And like we've established, elements in the same vertical group have similar but not identical chemical properties. And they form the same kinds of ions with the same charges. All right, if you've got the same electrons in the outer shell, if you lose those electrons, you're going to have the same charge as the other group members. So in group 1, for example, you've got H+, lithium+, sodium+, and K+ ions forming. And in group 7, you've got the -1 ions forming because they're actually gaining 1 electron. Each one of them is going to gain 1 electron. Now, there are 2 elements that are considered to be unusually placed on the periodic table. Hydrogen, for example, is weird, all right? It's got one electron, but it acts like a non-metal gas. It's technically a metal. It holds onto its electron reasonably strongly, but it does form +1 ions with other nonmetals. For example, hydrochloric acid. Chlorine's going to take its electron. You're going to get that charge happening. So it's in group 1, doesn't necessarily look like it. Helium is the other weirdo. All right? Helium's weird because it only has 2 electrons in its outer shell, but it's considered complete, as we know from our shell formula. Therefore, it reacts like the other elements in group 8 that also have full outer shells. It doesn't react with anything. Helium doesn't react because the group 8 elements are very unreactive, and we know them as the noble gases, all right, or inert gases, gases that won't do anything.
Something about that every other word wants to get to that, right?
Yes. The reason why we're forming ions is that we're trying to complete those shells and get to a noble gas state. But as soon as you do that, you'll have an imbalance of electrons and protons, and that's where your charge comes into it. So they'll never be truly neutral. But helium is. What do we use in balloons before helium?
Your breath. That is carbon dioxide.
I meant airships, I should say. Hydrogen, all right? Hydrogen reacts with fire. It's quite reactive. Helium does not. Who remembers the Hindenburg? We don't remember it, but you've probably seen it. It went up in flames. We now use helium, all right? It won't catch fire. And just as Pippa alluded to, or Philippa, sorry. Pippa is better? Good, I'll go with that. When atoms form ions, they do so to get that full outer shell structure like the noble gas. This is because the full outer shell is very stable and hence desirable. All right? So group 1, lose 1. Group 2, lose 2. And if you lose in electrons, you gain positivity. This is recorded. All right? Group 4 do neither. They share the electrons equally. That's the bell. I'll stop it there. I'll see you never? Thursday. I don't know. I'm still getting used to the timetable.